There is a question that almost everyone asks when they first hear that the universe is expanding. A question so natural and so obvious that it feels like it must have a simple answer. The question is, what is the universe expanding into? If the universe is expanding, if it is getting bigger, then there must be something outside it into which it is expanding. A void, a pre-existing space, a larger container. The universe is growing, so something must be receiving it. The expansion must be happening somewhere. I want to tell you that this question, while perfectly natural, contains a hidden assumption that is physically wrong. And the wrong assumption is not a minor technical point. It is a fundamental misunderstanding of what space is, what expansion means in the context of general relativity, and what the universe actually is. Correcting it does not just give you the right answer to one question. It restructures how you think about space, time, geometry, and existence in a way that makes modern cosmology coherent rather than mysterious. The wrong assumption is that space is a pre-existing container, a void that exists independently of the matter and energy within it, within which the universe sits and through which it expands. This is the Newtonian picture of space, the picture that Newton himself articulated: absolute space, existing independently of everything, providing the fixed background against which all motion takes place. In Newton's picture, asking what the universe is expanding into makes perfect sense. The universe is matter and energy, and it is expanding through the absolute space that contains it. But Newton's picture of space is wrong. Not approximately wrong. Not wrong at extreme velocities or at cosmological scales. Fundamentally and categorically wrong, as Einstein showed in his general theory of relativity. In general relativity, space is not a pre-existing container. Space is a dynamic physical entity shaped by matter and energy, capable of curving and stretching and expanding. Space is not the stage on which the play of physics is performed. Space is itself a performer, and its geometry, including its expansion, is determined by the content and distribution of matter and energy within it. The wrong assumption is that space is a pre-existing container, a void that exists independently of the matter and energy within it, within which the universe sits and through which it expands. This is the Newtonian picture of space. In Newton's picture, asking what the universe is expanding into makes perfect sense. The universe is matter and energy, and it is expanding through the absolute space that contains it. But Newton's picture of space is wrong. Not approximately wrong, not wrong at extreme velocities or at cosmological scales. Fundamentally and categorically wrong, as Einstein showed in his general theory of relativity. In general relativity, space is not a pre-existing container. Space is a dynamic physical entity shaped by matter and energy, capable of curving and stretching and expanding. And its expansion is not motion through a pre-existing container. It is the creation of new space. Before developing the physics, let me describe the observational history of the expanding universe, because the discovery itself is one of the great stories in the history of science and understanding. It helps clarify what expanding space means. The modern understanding of the expanding universe begins with Vesto Slipher, an astronomer at the Lowell Observatory in Arizona. Between 1912 and 1925, Slipher measured the spectra of spiral nebulae, the fuzzy objects that were at the time thought to be gas clouds within the Milky Way, but are now known to be entire galaxies. He found that most of these objects had redshifted spectra, meaning their light was shifted toward longer wavelengths, which in the Doppler interpretation meant they were moving away from us. By 1925, Slipher had measured the redshifts of 45 spiral nebulae, and 43 of them were receding. The pattern was suggestive, but not yet understood. In 1929, Edwin Hubble published the paper that established the expanding universe. Hubble had been measuring the distances to nearby galaxies using Cepheid variable stars, and he combined his distance measurements with the recession velocities measured from redshifts to produce the first Hubble diagram. The result was a clear, linear relationship. More distant galaxies were receding faster in proportion to their distance. The constant of proportionality is now called the Hubble constant, h0. Hubble interpreted this as galaxies flying away from us through space, a natural interpretation given the Newtonian background. But the correct interpretation, developed by Alexander Friedman in 1922 and independently by Georges Lemaitre in 1927, is that space itself is expanding. Friedman and Lemaitre both derived the expanding universe solution from Einstein's field equations applied to a homogeneous and isotropic universe. Their solutions predicted exactly the linear recession velocity proportional to distance that Hubble observed. Lemaitre also made a connection that Hubble did not. If the universe is expanding now, it was smaller in the past. Tracing the expansion backward leads to a singularity, a moment of infinite density and temperature at a finite time in the past. Lemaitre called this the primeval atom, and it is what we now call the Big Bang. The expanding universe is not just a description of the current state. It implies an origin, a beginning from a much denser and hotter state. Einstein was initially skeptical of the expanding universe solution, despite the fact that it followed directly from his own equations. When Friedman showed him the solution in 1922, Einstein wrote a note to a journal claiming Friedman had made a mathematical error, then retracted it when he realized the solution was correct. When Hubble's observations confirmed the expansion, Einstein called his introduction of the cosmological constant, which he had added to his equations to produce a static universe, his greatest blunder. He had made the cosmological constant 0 when his equations were telling him the universe was expanding. Now let me take you to the modern understanding of what expanding space means, because there is a specific sense in which the phrase create space that I want to develop carefully. This changes the question entirely. If space is not a pre-existing container but a dynamic entity created by and shaped by the universe's content, then the question, what is the universe expanding into, presupposes something that does not exist. There is no pre-existing space outside the universe. The universe is not expanding through anything. It is expanding, which means the space within it is increasing, which means new space is being created as the expansion proceeds. The universe is not growing into a larger container. It is creating its own container as it grows. I want to take you through the physics of this carefully, because the correct picture is not just philosophically interesting. It has specific, measurable, experimentally confirmed consequences that distinguish it from the Newtonian picture in ways that are testable and tested. The expansion of space is not a metaphor or a model. It is a physical fact about the geometry of the universe, described by Einstein's field equations and confirmed by every precision cosmological measurement ever made. Let me start with the geometry of space, because understanding what expanding space means requires understanding what space is in the relativistic picture. In Newton's physics, space is three-dimensional and Euclidean. The three dimensions of space are described by coordinates, and the distance between 2 points is calculated using the Pythagorean theorem, generalized to 3 dimensions. Space has this geometry everywhere and always, independently of what is in it. Matter exists in space, moves through space, interacts across space, but does not affect the geometry of space. Let me describe the Newtonian picture more precisely, because I think it is important to understand exactly what it says before explaining what replaces it. In Newton's Principia, published in 1687, he distinguished between absolute space and relative space. Absolute space is the true space, which by its nature remains always similar and immovable, independent of any external thing. Relative space is the measure of absolute space that we determine by the positions and motions of bodies. Absolute space is the pre-existing container. Relative space is what we observe. For Newton, absolute space was not just a philosophical convenience, it was a physical necessity. His laws of motion, specifically the distinction between inertial and non-inertial motion, required an absolute standard of rest. An object accelerating relative to absolute space experiences inertial forces. An object at rest or in uniform motion in absolute space does not. The rotating bucket experiment, in which water climbs the sides of a rotating bucket, was Newton's evidence for absolute space. The water climbs not because it is rotating relative to the bucket, but because it is rotating relative to absolute space. Einstein's general relativity replaced this picture completely. Space is not a pre-existing container, it is a dynamic physical entity. The geometry of space and of space-time is determined by the distribution of matter and energy through the Einstein field equations. The equations say, in essence, the curvature of space-time on the left side equals 8 pi g divided by c to the fourth times the energy-momentum tensor on the right side, geometry on the left. Matter and energy on the right, they determine each other. This is a fundamental inversion of the Newtonian picture. In Newton, space is the container and matter is the content. In Einstein, space and matter are partners, each determining the other. You cannot have space without matter and energy to shape it, and you cannot have matter and energy without the space-time geometry that responds to them. The curvature of space-time near the sun is what causes the planets to orbit in ellipses. This is not the sun exerting a force across space on the planets. It is the sun curving the space-time in its vicinity, and the planets following the straightest possible paths through that curved space-time. The paths are curved ellipses because the space-time is curved. In flat space-time with no matter, the straightest path is a straight line, and objects following it move in uniform straight line motion forever. The presence of matter curves space-time, and the straight lines in curved space-time are ellipses and parabolas and hyperbolas. General relativity has been tested with extraordinary precision. The bending of light by the sun, first measured during the 1919 solar eclipse by Eddington and collaborators, confirmed that light follows curved paths in curved space-time. The precession of Mercury's orbit, which deviated slightly from the Newtonian prediction and had been a puzzle since the mid-19th century, is precisely explained by general relativity's prediction of the space-time curvature near the sunday. Gravitational time dilation, the slowing of clocks in stronger gravitational fields, is measured every day in the GPS system. Gravitational waves predicted by general relativity in 1916 and detected by LIGO in 2015 are ripples in space-time geometry propagating at the speed of light. Every test of general relativity has confirmed its predictions. In Einstein's general relativity, space-time is a four-dimensional manifold whose geometry is determined by the distribution of matter and energy. The Einstein field equations, the central mathematical result of general relativity, relate the curvature of space-time to the energy-momentum content. Curvature is not just a metaphor for the effect of gravity. It is the physical mechanism of gravity. Freely falling objects, including light, follow the straightest possible paths through curved space-time, and we perceive these curved paths as the effects of gravitational attraction. The FLRW metric is the space-time geometry of a homogeneous and isotropic universe, a universe that looks the same in every direction and at every location when averaged over large scales. The metric has a single time-dependent function. The the scale factor AT that describes how distances in the universe change with time. When the scale factor increases, distances between objects increase. The universe expands. When the scale factor decreases, distances decrease. The universe contracts. The crucial feature of the FLRW metric is that the expansion is not the motion of galaxies through space. The galaxies are, on average, at rest in the coordinates of the FLRW metric. They are not moving. The space between them is growing. The galaxies are being carried apart by the expansion of the medium they inhabit, not flying through a pre-existing space. This distinction has specific and testable consequences. If galaxies were moving through space, their velocities would be limited by the speed of light. Nothing can move through space faster than c. But if it is space that is expanding rather than galaxies moving through space, then the recession velocity of distant galaxies, the rate at which the distance between us and them is increasing, can exceed c. And indeed it does. Galaxies beyond the Hubble radius, approximately 14 billion light years, are currently receding from us faster than the speed of light. Their light is still traveling toward us, but the space between us and them is expanding faster than the light can cross it. This is not a violation of special relativity. Special relativity says nothing can move through space faster than c. It says nothing about the expansion of space itself. The recession of distant galaxies is not motion through space. It is the expansion of space. The distinction is physically meaningful and observationally confirmed. Let me give a specific analogy that I think captures the correct picture better than the common explosion analogy. Imagine the surface of a balloon being inflated. Draw dots on the surface to represent galaxies. As you inflate the balloon, the dots move apart. But they do not move across the surface of the balloon. They are stationary on the surface. It is the surface itself that is expanding, and the expansion carries the dots apart with it. Now notice that every dot sees every other dot moving away from it. There is no center of expansion on the surface of the balloon. Every dot is equally the center from its own perspective. If you are on one dot, all the other dots are moving away from you, and the more distant dots are moving faster than the nearby ones, in exact proportion to their distance. This is Hubble's law. V equals h times d, where v is the recession velocity, h is the Hubble constant, and d is the distance. Notice also that the surface of the balloon is not expanding into anything. The surface is a two-dimensional space, and it is not embedded in a larger two-dimensional space. It is a curved two-dimensional surface, and its expansion is a property of the surface itself, not a motion into a larger space. When the balloon is inflated, the two-dimensional surface of the balloon grows. More two-dimensional space is created. The two-dimensional creatures on the surface are not moving into a pre-existing larger two-dimensional space. They are experiencing the creation of more of their own space. The analogy is imperfect in one important way. The surface of a balloon is a two-dimensional surface embedded in a three-dimensional space. You can see the balloon from outside, from the three-dimensional perspective. The universe is not embedded in a higher dimensional space in this way, as far as we know. The three-dimensional space of the universe is the whole of space, not a surface embedded in a larger space. When the universe expands, there is no higher dimensional outside from which you could observe the expansion. The universe is everything. There is no outside. This is the deep answer to the question, what is the universe expanding into? The universe is not expanding into anything. It is expanding. The expansion is a property of the universe's geometry, described by the scale factor in the FLRW metric. The space within the universe is increasing, new space is being created, but there is no pre-existing space into which it is expanding. There is only the universe. and the universe is getting bigger by creating more of itself. Now let me take you to something that I think is the most counterintuitive and the most profound consequence of the expanding space picture, which is the question of whether the universe is infinite or finite. If the universe is finite in spatial extent, it has a total amount of space. As the universe expands, this total amount of space increases. New space is being created. The universe is getting bigger not by growing into something else, but by containing more space. If the universe is spatially finite and closed, like the surface of a sphere but in 3 dimensions, then expanding the universe increases the total volume of the 3-dimensional sphere. The sphere is getting bigger without growing into anything, in exactly the same way that inflating a balloon increases the area of the 2-dimensional balloon surface without the surface growing into a larger 2-dimensional space. If the universe is infinite in spatial extent, the situation is even stranger. An infinite universe that is expanding is also infinite. There is no size to compare before and after. The universe is infinite before the expansion and infinite after. But the expansion is still real and measurable. Even in an infinite universe, the distance between any 2 specific points increases as the universe expands. The local expansion is real even if the global expansion does not change the universe from finite to infinite. Current observations suggest that the universe is either flat or very nearly flat, meaning its geometry is consistent with Euclidean geometry on the largest scales. The Planck satellite measured the curvature parameter of the universe to be consistent with 0 to within 0.4%. A flat universe can be either finite, like a 3-dimensional torus, or infinite, like an infinite, flat 3-dimensional space. The current observational data cannot distinguish between these possibilities. If the universe is infinite, it has always been infinite, even at the Big Bang. The Big Bang singularity was not a point from which the universe exploded outward into empty space. It was a state in which every region of the infinite universe was arbitrarily dense and hot. An infinite universe expanding from an infinitely dense state. The expansion did not begin with a small universe growing larger. It began with every point in the infinite universe at infinite density and has proceeded with every point in the infinite universe getting less dense as the distance between points increases. This is deeply counterintuitive because it contradicts the image of an explosion from a single point. But the image is wrong. The Big Bang was not an explosion from a point in a pre-existing space. It was the beginning of space itself, simultaneously everywhere in the universe with no center and no edge. If the universe is finite, the situation is more like the balloon analogy. A finite universe that was once very small has expanded to become much larger. The early universe was small, the current universe is large. In between, space was created continuously as the universe expanded. The total amount of space has increased by an enormous factor over 13.8 billion years. And the universe is currently creating more space with every passing second, driven by dark energy. In either case, finite or infinite, the answer to the question, what is the universe expanding into, is the same: nothing. The expansion is a property of the universe's internal geometry, not a growth into an external space. There is no external space. Now let me take you to the observational evidence for this picture, because the expansion of space is not just a theoretical construct derived from general relativity. It is directly observed and has been confirmed by multiple independent methods. The first evidence is the redshift of distant galaxies. When light travels through expanding space, its wavelength is stretched along with the space. A photon emitted by a galaxy at a specific wavelength arrives at Earth with a longer wavelength shifted toward the red end of the spectrum. This cosmological redshift is the primary observational signature of the expanding universe. The redshift is not a Doppler effect, though it is often described as one in the low velocity limit. The Doppler effect arises from the motion of the source through space. The cosmological redshift arises from the expansion of space during the photon's journey. The two effects have different mathematical properties at large distances and high redshifts. The relationship between redshift and distance, the Hubble diagram, has been measured for galaxies over a range of billions of light years using type Ia supernovae as standard candles. The measurements confirm the predictions of the FLRW model with extraordinary precision. The specific form of the Hubble diagram, including the deviation from a simple linear relationship at large distances due to the effects of dark energy, matches the theoretical predictions of the expanding universe model. The second evidence is the cosmic microwave background. The CMB is the afterglow of the hot early universe, the thermal radiation emitted when the universe first became transparent approximately 380,000 years after the Big Bang. The CMB has been stretched to microwave wavelengths by the expansion of space in the 13.8 billion years since it was emitted. It has a perfect black-body spectrum at a temperature of 2.725 Kelvin. The specific properties of the CMB, including its near-perfect isotropy and the tiny temperature fluctuations that reflect the density perturbations of the early universe, are precisely predicted by the expanding universe model. The third evidence is Big Bang nucleosynthesis. The abundances of the light elements, hydrogen, helium, deuterium, and lithium, produced in the first 3 minutes of the universe depend on the specific history of expansion and cooling. The observed abundances of these elements match the predictions of the standard Big Bang model with extraordinary precision, confirming that the universe expanded from a hot, dense state in the specific way the FLRW model describes. All three of these lines of evidence, and many others, are consistent with the picture of a universe whose space is expanding from an initial hot, dense state, not a universe of galaxies flying through a pre-existing space. The expanding space picture is not just theoretically preferred, it is observationally confirmed. Now let me take you to something that I think is the most counterintuitive and the most profound consequence of the expanding space picture, which is the question of whether the universe is infinite or finite. If the universe is finite in spatial extent, it has a total amount of space. As the universe expands, this total amount of space increases. New space is being created. The universe is getting bigger, not by growing into something else, but by containing more space. If the universe is spatially finite and closed, like the surface of a sphere, but in 3 dimensions, then expanding the universe increases the total volume of the 3-dimensional sphere. The sphere is getting bigger without growing into anything, in exactly the same way that inflating a balloon increases the area of the 2-dimensional balloon surface without the surface growing into a larger 2-dimensional space. If the universe is infinite in spatial extent, the situation is even stranger. An infinite universe that is expanding is also infinite. There is no size to compare the before and after to. The universe is infinite before the expansion and infinite after. But the expansion is still real and measurable. Even in an infinite universe, the distance between any two specific points increases as the universe expands. The local expansion is real, even if the global expansion does not change the universe from finite to infinite. Current observations suggest that the universe is either flat or very nearly flat, meaning its geometry is consistent with Euclidean geometry on the largest scales. A flat universe can be either finite, like a torus, or infinite, like an infinite plane. The current observational data cannot distinguish between these possibilities. If the universe is flat and infinite, it has always been infinite, and it will continue to be infinite as it expands. If the universe is flat and finite, it is getting larger, creating new space, without growing into anything. In either case, the answer to what is the universe expanding into is the same: nothing. The expansion is a property of the universe's internal geometry, not a growth into an external space. There is no external space. Let me now address the question of what is creating the expansion, because understanding the cause of the expansion illuminates the mechanism by which space is created. The expansion of the universe is described by two Friedmann equations derived from Einstein's field equations applied to the FLRW metric. The first Friedmann equation relates the expansion rate, the Hubble parameter, to the total energy density of the universe. The second relates the acceleration of the expansion to the pressure and energy density of the universe's content. In the early universe, the dominant form of energy was radiation, the hot photons and other relativistic particles of the Big Bang plasma. Radiation exerts a positive pressure which slows the expansion. As the universe expanded and cooled, the radiation density fell faster than the matter density, and eventually matter came to dominate. Matter also slows the expansion, because gravity pulls things together, and more matter means more gravitational deceleration. If the universe contained only matter and radiation, the expansion would be decelerating. It would slow down over time, possibly stopping and reversing into a big crunch, or expanding forever but at a decreasing rate. For most of the 20th century, this is what cosmologists expected. Then, in 1998, the Supernova Cosmology Project and the High-Z Supernova Search Team, using observations of distant type Ia supernovae, discovered that the expansion of the universe is accelerating. The universe is not just expanding, it is expanding faster and faster. Something is driving the acceleration. That something is dark energy. Dark energy is a form of energy associated with the vacuum of space, a constant energy density that does not dilute as the universe expands. Unlike matter and radiation, dark energy has negative pressure. In the Friedmann equations, negative pressure contributes to acceleration rather than deceleration. When the dark energy density becomes the dominant term in the Friedmann equations, the expansion accelerates. The current best measurement of the dark energy density is approximately 68% of the total energy density of the universe. Matter contributes about 27%, almost entirely dark matter. Ordinary matter, the atoms that make up stars and planets and people, contributes only about 5%. The universe is dominated by things we do not fully understand. Dark energy and dark matter together make up 95% of the total energy content. Dark energy is consistent with Einstein's cosmological constant, a term he added to his field equations in 1917 and later called his greatest blunder. When he believed the universe was static, he added the cosmological constant to counteract gravity and produce a static universe. When Hubble discovered the expansion, Einstein removed it. But dark energy turns out to have exactly the mathematical form of the cosmological constant, and its measured value is consistent with what you would predict for a constant energy density of the vacuum. The cosmological constant was not a blunder, it was a prediction. The dark energy is what is creating the accelerating expansion. But calling it a cause is somewhat misleading. Dark energy is not a source of new space in the sense that it is producing space from somewhere else. It is a property of space itself, an energy density associated with the vacuum. As new space is created by the expansion, new dark energy comes with it, which is why the dark energy density remains constant even as the universe expands. The dark energy and the expansion are aspects of the same physical process. The dynamics of space-time geometry as described by Einstein's field equations with a non-zero cosmological constant. Now let me explain what is causing the expansion, and specifically the acceleration, because understanding the cause illuminates the mechanism by which space is created. The expansion of the universe is described by two Friedmann equations derived from Einstein's field equations applied to the FLRW metric. The first relates the expansion rate to the total energy density. The second relates the acceleration to the pressure and energy density of the universe's content. In the early universe, radiation dominated. As the universe expanded and cooled, matter came to dominate. For most of the 20th century, cosmologists expected the expansion to be decelerating due to gravity. Then in 1998, two independent teams using type Ia supernovae as standard candles found the distant supernovae fainter than expected. The expansion was not decelerating, it was accelerating. This was completely unexpected. Both teams checked their results extensively before publishing. When both found the same result independently, the conclusion became unavoidable. Perlmutter, Schmidt, and Rees received the Nobel Prize in 2011 for this discovery. Dark energy is what drives the acceleration, a form of energy associated with the vacuum of space, a constant energy density that does not dilute as the universe expands. Its equation of state parameter W equals approximately -1, the value for a cosmological constant. As new space is created by the expansion, new dark energy comes with it, which is why the dark energy density remains constant while the universe grows. The total amount of dark energy in the universe increases as the universe grows. The cosmological constant was added by Einstein in 1917 to produce a static universe, then removed when Hubble discovered the expansion. Einstein called it his greatest blunder. But dark energy has exactly the mathematical properties of the cosmological constant. The greatest blunder was, in fact, a prediction. The theoretical vacuum energy density calculated from quantum field theory is approximately 120 orders of magnitude larger than the observed dark energy density. Why is the observed value so much smaller than the theoretical prediction? This is the cosmological constant problem, one of the most severe discrepancies in all of physics. It has no accepted solution. Now let me take you to the most personally significant aspect of the expanding space picture, which is what it means for the future of the universe and for our relationship to the rest of the cosmos. The accelerating expansion driven by dark energy has a specific and extraordinary implication for the future. As the expansion accelerates, the observable universe shrinks. Not in the sense that the universe gets smaller, but in the sense that more and more of the universe recedes beyond our cosmic event horizon, the boundary beyond which light will never reach us. Let me be precise about what the cosmic event horizon is, because it is different from the particle horizon, and the distinction matters for understanding the future. The particle horizon is the boundary of the observable universe, the farthest distance from which light could have reached us in the 13.8 billion years since the Big Bang. It currently lies approximately 46 billion light years away. Galaxies beyond the particle horizon have not yet had time to send us any signals. But if the universe were not accelerating, their light would eventually reach us, given enough time. The particle horizon expands outward as the universe ages. The cosmic event horizon is different and more severe. It is the boundary beyond which signals sent to us right now will never reach us, because the space between us and those signals is expanding faster than the signals can travel. The cosmic event horizon currently lies approximately 16 billion light years away. Galaxies currently beyond the event horizon are receding so fast that no signal they send today will ever reach us, even in principle, even given infinite time. They are permanently beyond our reach. As the expansion accelerates, the event horizon does not expand. It contracts or stays approximately constant. This means that galaxies currently inside our event horizon will, over time, cross the horizon and become permanently unreachable. A galaxy at 10 billion light years today is inside our event horizon, and we can receive signals from it. But as dark energy drives the acceleration, that galaxy's recession velocity will increase, and eventually it will recede beyond the event horizon and disappear from our cosmos. The timescale for this process is billions of years. It is not immediate. But on cosmological timescales, the isolation of the local group is inevitable. Every galaxy outside the gravitationally bound local group will eventually recede beyond the event horizon and vanish from our observable universe. The local group itself, held together by gravity, will gradually merge over the next few billion years, eventually coalescing into a single large elliptical galaxy. That merged galaxy will be surrounded by an ever-expanding void, with the rest of the universe permanently beyond the event horizon. Currently, the observable universe extends to approximately 46 billion light years. Galaxies at that distance are receding from us at speeds approaching c due to the expansion of space. Galaxies beyond that distance, the vast majority of the universe, if the universe is much larger than the observable part, are already beyond our event horizon, receding faster than light, and forever invisible. This is one of the most sobering consequences of the accelerating expansion. In the far future, billions of years from now, the Milky Way will be gravitationally bound to the other members of the local group, but every galaxy outside the local group will have receded beyond the event horizon. The observable universe will consist of only the local group, surrounded by an empty, expanding void in every direction. This is one of the most sobering consequences of the accelerating expansion. In the far future, intelligent observers in the Milky Way, if any exist, will have no observational evidence for the expanding universe. The galaxies that we use to measure the expansion, the Type Ia supernovae that reveal dark energy, will all have receded beyond the horizon and vanished. The CMB will have been redshifted to undetectably low temperatures. The evidence for the Big Bang will have disappeared. If those future observers have not inherited our knowledge of the universe, they will have no way of knowing that the universe began with a Big Bang, that it is expanding, that it contains hundreds of billions of galaxies. They will live in what appears to be a single static island of stars surrounded by eternal darkness. They will have no way of discovering the expanding universe because the universe will have expanded beyond their ability to observe. This is a humbling thought. Our current ability to observe the universe's expansion, to measure the Hubble constant, to detect the cosmic microwave background, to observe distant galaxies, is a feature of the specific epoch of cosmic history we inhabit. It is a window that is closing. The universe is generous with its secrets in this era, but in the era of accelerating expansion, it is becoming more secretive. We are fortunate to live when we do. Let me close with something that I think is the most important thing to understand about the expansion of space and what it reveals about the nature of the universe. Before I do, let me address one more aspect of the expanding space picture that I think deserves explicit attention: the experience of a photon traveling through expanding space. When a photon is emitted by a distant galaxy and begins its journey toward Earth, it travels at c in its local space. But the space it is traveling through is expanding. This has a specific and dramatic effect on the photon's journey. Imagine a photon emitted from a galaxy that is, at the moment of emission, 1 billion light years away. Naively, you might think the photon would take 1 billion years to reach us. But the space between us and the galaxy is expanding during the photon's journey. By the time the photon reaches us, the galaxy that emitted it is farther away than 1 billion light years. because space has expanded during the journey. The photon has had to travel through more space than the initial distance would suggest. For photons emitted from very distant galaxies, this effect is dramatic. The CMB photons were emitted when the universe was approximately 380,000 years old, and the source was approximately 42 million light years away. But the space between us and those photons has expanded enormously during the 13.8 billion years of the photon's journey. The source of the CMB is now approximately 46 billion light years away, and the photons have traveled a co-moving distance of approximately 46 billion light years. The expansion of space also stretches the photon. The wavelength of the photon is proportional to the scale factor at the moment of reception divided by the scale factor at the moment of emission. For CMB photons, the scale factor has grown by a factor of about 1,100 since the moment of emission. This means CMB photons have been stretched to 1,100 times their original wavelength, redshifted from the optical range into the microwave range. The temperature of the CMB, 2.725 Kelvin, is the original temperature of the photon-baryon plasma at recombination, approximately 3,000 Kelvin divided by 1,100. Every photon that has traveled to us from a distant galaxy carries in its wavelength a record of how much the universe has expanded since the photon was emitted. The redshift is a direct measurement of the expansion of space during the photon's journey. When we measure the redshift of a galaxy, we are measuring the ratio by which the universe has expanded since the light we are seeing was emitted. This is what the expansion of space means at the level of individual photons. It is not an abstraction. It is a physical effect that stretches light as it travels, imprinting the expansion history of the universe on the wavelengths of every photon that reaches our telescopes. The next time someone asks you what the universe is expanding into, you can tell them nothing. And then you can explain why that is not just an answer to a question, but a statement about what space is, what the universe is, and what it means for something to exist in a universe that creates its own space as it grows. The universe is not expanding into space, it is creating space as it expands. The expansion is a property of the universe's internal geometry, not a growth into an external container. There is no outside. The universe is everything. Everything is the universe. And the universe is expanding by creating more of itself, more space, more room for the matter and energy within it to spread out, more room for the entropy to increase, more room for the thermodynamic engine of the Big Bang to continue running. If this changed how you think about the expansion of the universe, if the question, what is it expanding into, looks different after understanding what space actually is in general relativity, tell me in the comments. Tell me whether you find the balloon analogy helpful or misleading, and what would be a better one. Tell me whether the disappearance of the observable universe in the far future as galaxies recede beyond the event horizon changes how you feel about the work of observational cosmology today. And subscribe if you want to keep going into the places where the basic facts of physics reveal the structure of reality to be far stranger and more extraordinary than the common picture suggests.